تعرف انه الخلاف الكلاس حسب على الخط على البريتندنت هو participation 10% or 15 ما هي اللي قبل الكلاس عشان الثاني كيف الكلاس مش إلا والله إلا لا يا عم كنت المفروض تستخدم الوقت اللي فات.
Hey, how's it going?
How are you doing today?
Good. How are you guys? How's your weekend?
Pretty good. Good. Actually, I don't know. I don't know what I did.
It all becomes a blur as soon as Monday hits.
Did a lot of sleeping.
That's good. That's good. Get your sleep now before it gets crazy.
Oh, I did the answer activity.
Okay, it's good. It's good.
That's like most of my Saturday. Thank you for that.
It's the same one. You've done this is your third time doing this activity, right?
Very spirit activity. It's so fun going back and being like, okay, now change the whole thing.
That's the most annoying one because you have to go back to the design model. Yeah, I know.
I love it actually.
I can feel it in the voice.
In like the note section of the school, like there's a note out of notes of this course, and very similar to the FEM course.
Not really. So 541 we did theory, so there was a lot of math in that one. This one's all about the application. So we're talking about you've probably seen some of it. At least the concept should be similar, but it's more about how do we best use ANSYS to the best of its ability.
Oh, that's really cool. Okay. Thank you.
People generally like this class more than 541. 541 I don't get very good reviews for this class. People.
Why are you not guessing?
All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Good. Has it set in yet that the spring semester has begun? That we're no longer on break anymore? Holidays are done. Okay, good. It's better. You guys are doing better than me. I still feel like I should be on break, but okay. So today's going to be a lecture day. Actually, both of the lectures this week are going to be lectures, and so generally the format for this class is that every other week we're going to have an ANSYS activity, and then in between the ANSYS activities we're going to be talking about not really any theory. This class is very application driven, but just we're going to have lectures talking about the different basically how to get the most out of ANSYS. there are important concepts there for sure. So we're gonna talk about certain concepts of FEA, how that relates to ANSYS and you know, how to best kind of go about its things. So you know, last Thursday we did our first ANSYS activity. You know, so I think for a lot of people, it's kind of just it was a little bit fast. You know, I was kind of telling you to do things and you know, not really explaining how a lot of these things work. That's okay. That was by design. And so the idea is that over the next, you know, well, I guess full semester, that you know, a lot of the decisions, a lot of these settings, a lot of the things that we are doing in the activities will start to make more sense. And then you'll be able to apply that same logic to other future problems. Okay. That's basically my goal with this class. My goal with this class is, you know, by the end of the class, you'll have a very full kind of complete understanding of how to use ANSYS as a tool for a very wide variety of problems, and then you'll be ready to apply it to your, you know, whatever you're working on, either at work, maybe you're applying it for research here or on a project, and you'll have kind of, you know, the knowledge to do that, you know, with confidence and can defend all of your decisions. Okay. All right, so the plan for today is, you know, we're just going to do a very brief 1-day introduction to kind of the theory behind FEA. Okay, so this class is not a theory class, and so this is probably the only day we're going to be talking about it. But I still think it's useful to know at least kind of what ANSYS and what other FEA softwares are trying to accomplish underneath the hood, or basically how they take your problem and turn it into a math problem that the computer can solve. Okay. So we'll be talking about, you know, what finite elements just does as a method, how that kind of allows itself to be used by computers really well. We'll go over the definition of a boundary value problem, and then we'll go over what I call kind of the global linear system at the end of the class today. Okay. By the way, so this is how I usually lecture in this class, and so you know, if we're not doing an ANSYS day, this is kind of what I'm going to do. So I have my iPad here. I have an Apple Pencil. I'm streaming it on Zoom, as people on Zoom can know already. Okay. And then, you know, this is kind of like my pseudo whiteboard. It's not as fun as using the real whiteboard. The real whiteboard, you know, I can kind of walk across the whole classroom. I haven't done that in, you know, 5 years at this point. But you know, I think it's useful for this. Okay. All right. Any questions I can answer before we get started for today? Okay, all right, so let's go ahead and get started. So the topic for today, I call it the theory behind FEA. Okay. All right, so like I mentioned, you know, this class is pretty much almost entirely application driven, and so you know, we'll be learning about ANSYS, you know, for the entire semester, but it's still useful, especially if you've never seen finite elements before, you've never taken a course in finite elements before, to at least kind of understand what's going on, at least at a very broad level, so that you can kind of, you know what the computer is doing. Okay. All right. So like I mentioned, finite element analysis. Okay, or FEA for short. Finite element analysis actually doesn't have anything to do with computers at all. Nowadays, we often associate it together with computers because of softwares like ANSYS and softwares like Abacus or solid simulation. But you know, in the very early days, finite element analysis started as just a subject or just a topic of research in applied mathematics. Okay. And so it wasn't even in engineering at all, although you could make the argument that applied math is kind of the weird second cousin of engineering. And so the idea with FEA was to it was a mathematical technique to take a differential equation and transform it into an algebraic system of equations. And so, FEA on by itself actually didn't find the solution to a problem. It just took your problem and transformed it into another problem. Okay. All right. So, kind of symbolically, it kind of looks something like this. So you would take a differential equation. So you can take any differential equation. I'm going to use the heat equation as an example here. Okay. So let's say we take the heat equation. Okay. It doesn't have to be the heat equation. That's just usually the first differential equation that comes to mind. Okay. So here we have a differential equation, in this case, a partial differential equation. Okay. If you've already taken 438 or 538, that hopefully should be familiar to you. Okay. And then through finite element analysis, okay. So FEA kind of forms this bridge in the middle. Okay. So FEA is not the solution itself. It's just a way of transforming the problem. Okay. Okay. And so through FEA, you can take this differential equation and get a corresponding system of algebraic equations. Okay. So, on the right here, you can see I've displayed the algebraic equations in matrix form, right? Anytime you have a system of algebraic equations that are linear and constant coefficient, you can transform it into a matrix, okay? And that's often convenient if you have, usually if you have more than 5 or 6 equations, usually it's more convenient to display it in matrix form, okay? And so that's something you're going to see throughout today as well, okay? So you're going to see multiple matrices. And the reason I use matrices here is actually very important for FEA as well, because this is not usually a small system of equations. So this is not 5 equations, 5 unknowns, not even 10 equations, 10 unknowns. We're talking about thousands of equations, thousands of unknowns, or even millions of equations, billions of unknowns. Okay, so this matrix here can have anywhere between 10,000 to 1 million equations. Okay? Just as a starting point. Okay? Right, so these are not kind of trivial systems. And so the idea is that, after you transform the equation with FEA, you get this algebraic system of equations, you solve this algebraic system of equations, the solution to that algebraic system of equations is equivalent to the original differential equation, or at least it's very close to it. Okay? Okay? And so if you don't want to solve a differential equation, but instead you want to solve an algebraic equation, you can use FEA, transform the problem to an algebraic problem, solve the algebra problem, and then you would have your solution from it. Okay. So when FEA was first introduced, it was not very well received because, when FEA was first kind of proposed as a theory, this was kind of before the age of computers, before we knew that computers were good at solving, these kinds of systems. And so, people proposed FEA, they said, look, we can take a differential equation and we can transform it into an system of equations. And the general response is, for people is like, great. Now, instead of having a really difficult differential equation to solve, now we have a really difficult algebra problem to solve. And so you've solved nothing, right? And so this in its first state, this was not very useful to people. So this was not useful by itself. Okay. And so it kind of just existed as a novelty. It kind of existed kind of as a cool concept, but it didn't really kind of take off as something that's actually practical. Okay. And it's easy to kind of look at this in hindsight and be like, those people were fools. How could they not see that this was great, right? Turns out, a lot of ideas in the academic community are just terrible ideas. And so, this was not an unreasonable reaction by most people at the time. Okay. It wasn't until that, kind of in the 70s and kind of a lot more in the 80s that, computers and the idea of using computing to solve math problems really kind of started to take off. Okay. Okay. Because there's one thing, well, there's a lot of things that computers are good at, but one particular thing that computers are actually really good at doing, and actually, it's actually very relevant today as well, is that computers are actually really good at solving algebra problems. Okay. In particular, computers are very good at solving very large algebra. So, systems like what you get from FEA. So systems with, 100,000 equations, 1,000,000 equations, computers are actually really good at solving those. In fact, there is a whole branch of high performance computing research that's still being done today on the concept of what's called a linear solver. So a linear solver is the particular algorithm that a computer will use to solve a large system of linear algebraic equations. Just as an aside, this is a very, very hot topic right now because if you've been kind of paying attention to the news lately, there's been a new AI company or I guess an AI tool that's been released called DeepSeek from China. And they're able to basically replicate a lot of our AI technology with kind of a fraction of the cost. And so one thing that people suspect is that, they're probably using a very, new and kind of revolutionary linear solver to kind of process all this AI data. That's the theory, and but you don't really know at this point. Right? So linear solvers is actually one thing I hope to kind of to get to in this class, probably near the end. Linear solvers is actually something that you can choose in ANSYS as well, okay? And it does actually affect your solution. So that's something kind of good. Okay? But as linear solvers and as computers start to kind of show that they can solve these very large systems of equations, people start to say, hey, remember that FEA thing that everyone thought was stupid, like 10 years ago? Like what if we actually start to use that and combine that with computing? And so that's kind of when FEA started to take off. So, computers aren't really that great at solving differential equations by itself. That's not something that can be done at this point. But if you take your differential equation, transform it into an algebraic system, solve it in a computer, then all of a sudden, you have, a very, very powerful tool. Okay. And it turns out most engineering systems, when you talk about its physical behavior, whether you're talking about a structural system, a thermal system, or a fluid system, electromagnetic system, the governing laws of conservation of mass, momentum, energy, pretty much all of them are differential equations. Okay. So when you have these physical systems, they're governed by differential equations. Normally, these differential equations are too difficult to solve, especially when you talk about, you have complex geometries, complex boundary conditions, complex loading, time varying solutions. Before we could only really solve these differential equations kind of in very simple cases. But this idea of, using FEA, taking the differential equations, transforming into an algebraic system, use the computer to solve that, then all of a sudden, things start to kind of fall into place. So the general kind of flow chart, which is kind of still used today for FEA, kind of goes like the following. So usually when you're doing any kind of analysis or design, you start with some physical engineering system. And I say physical, but this could also be electromagnetic. It could also be thermal, fluids, right? Anything that's governed by differential equations. Okay. I just say governing differential equations. What you can do at that point is you can take those differential equations on your complex system, use FEA to transform it into an algebraic system of equations. Then when you have your algebraic system of equations, it's normally very large and you can't solve it by hand, but a computer can do it. Okay, so then you then pass that problem to a computer. So then through use of a computer, through the use of a linear solver, you then get a solution to that algebraic system. Okay. At this point, you have kind of you have the solution to your problem, but it's very raw. It's kind of just raw data. And so there's a little bit more processing that has to be done. So this is usually done in the computer itself, right? We won't talk too much about post-processing in this class, but just know that there is a process that needs to be done to go from raw solution to kind of the color contours that you view within ANSYS itself. Okay, so this step is often called post-processing. And so that'll give you the results, okay? And then from those results, you can then pass them to an engineer to do any kind of design and analysis. So maybe he wants to tweak the design, or maybe he wants to analyze a certain part, compute the stresses. So that's kind of when you start to do kind of the real kind of engineering work. Okay. And then based on the design and analysis, you can then improve your original engineering system. Okay. So now, with the development of FEA and the development of computing, kind of this new paradigm and kind of this new way of kind of doing engineering work that utilizes a computer, really started to form, right? And this kind of cycle here is pretty, I would say, emblematic of a lot of modern engineering design and analysis that utilizes computers, utilizes tools, to do this stuff for you. Okay? And of course, within this process, you have things like SolidWorks. You would use SolidWorks to modify your design to get the drawings for it. And so it's all kind of within kind of one integrated system that FEA kind of helps facilitate. Okay? All right. Any questions on this? Cool. All right. So I like telling this story just because, even though, a lot of times when scientists or when researchers come up with a new idea, yeah, a lot of things seem really stupid at first. But a lot of times, the technology just may not be there to kind of utilize it, effectively. And so I think you're seeing that with kind of a lot of machine learning and AI stuff as well. So before, machine learning has been around for a long time. I remember people were talking about it basically all through when I was in school. But it's only now that we have these really powerful NVIDIA chips that it's really becoming kind of part of our everyday life. Okay, so let's move on. All right, so the next thing I want to talk about is the concept of a boundary value problem. Okay. So a boundary value problem is basically an expression of the underlying, I would say, mathematical problem that an FEA hopes to solve or strive to solve. So kind of at the heart of every finite element analysis, even the activity that we did last Thursday is an underlying boundary value problem. Okay. Um, and I'm bringing this up just because, whenever you do a new FEA or finite element analysis, it's always useful to think about, what's the underlying boundary value problem. Because it kind of helps to kind of organize, it helps to kind of organize your thoughts in that way. It helps you kind of determine the boundary conditions and what equations to solve. And a lot of times, it's actually very useful to kind of write it down as well. Okay. Okay. So there are three parts to a boundary value problem. Part one is the domain. Okay. Part 2 is the governing equations. Okay. And part 3 are the boundary conditions. Okay. We're going to go through each of these parts. Okay. All right, so let's talk about the domain first. So the domain of a finite element analysis is simply just the geometry on which we want to solve the equation, or the geometry that we want to perform the analysis. It defines things, very simply, like, it defines the volume of the analysis, and defines the surface area. It also gives kind of, all the surfaces and all of the places where we can apply things like boundary conditions and things like that. Okay. It's the starting point. So before you start an FEA analysis, you need to have some kind of geometry or some kind of domain, which, again, seems obvious. But it also kind of brings up some very interesting questions of, what should be part of your domain to begin with. Okay, so the domain often is defined for practical FEAs, defined by the CAD file that you're using for the analysis. Okay. And so let me go ahead and draw kind of a generic figure here. And so, of course, the class of all possible domains that you can do in FEA is ginormous, right? So you can run FEA on almost anything that you have a CAD file. And so to represent all of those possible geometries, I've drawn here for you an arbitrary potato. Okay. Okay. And so I've drawn the potato here for a good reason, because oftentimes, we kind of differentiate between two areas of our domain. Okay. We have the interior of the domain. So the interior domain, I often give the symbol omega. Okay. And then we have the exterior of the domain as well. Okay. So the exterior of the domain is often given the symbol partial omega. So we often kind of differentiate between those two, and oftentimes we make that kind of differentiation just because the exterior is often where we apply boundary conditions. Okay. We'll talk about this in the coming weeks as well, but the exterior, you often need to use a different meshing scheme for the exterior. Okay. So it's good to kind of differentiate, which parts of your geometry are the interior and which are the exterior. Okay. Okay. So, why is it useful to think about the domain? Well, it's useful to think about the domain in the sense of, if you have some very complex part, you have some very complex geometry, it's always useful to think about, what parts of the geometry do I actually need to include in my analysis? Because oftentimes, what you're going to see is that, if you get a CAD file that you produce in SolidWorks, right? A CAD file that you produce in SolidWorks often has very different goals than a CAD file that you're going to use for FEA. So a lot of times, when you get CAD files, so let's say that, you're an FEA engineer working for a company, you get a CAD file passed to you from the design engineer. Oftentimes that CAD file is going to have way too much information than you need to actually run your analysis. Okay, what do I mean by that? So oftentimes, one thing that you're always going to be fighting with FEA is this idea of, how many mesh elements do I need, right? So the more mesh elements that you have, the more expensive your simulation is going to be, okay? Usually when you produce a CAD file that's going to be used for design, oftentimes you're going to include every aspect of that design as possible, right? And that includes all the really tiny details or maybe all the kind of superficial kind of stuff, just because it's a CAD file. It's you're designing something to be made, right? When you run an FEA, a lot of times you're running kind of stress analysis on parts that are going to be bearing weight or going to be bearing load. Okay. A lot of times, all those really kind of small features that you're going to have kind of on the exterior of your CAD file or of your geometry are not really going to be important in the analysis. But they're still going to take up a lot of cost. So it takes a lot of energy, it takes a lot of kind of computing power to mesh it, to solve it on there, right? And so, one thing we're going to talk about a lot in this class is, how do what are kind of the best ways to take a geometry and kind of just strip it to kind of what are the most important parts and then run your analysis on that. And you're going to, a lot of times, just by doing that simple step, you're going to save yourself a lot of cost, a lot of time, a lot of energy, rather than trying to simulate every kind of little thing. Okay. All right. Any questions on this so far? Good. Okay, so domain, oftentimes pretty obvious, probably not something we're going to think about, for a good part of this class. But once you guys start doing the projects, midterm project, final project, then it's something that, you should be kind of thinking. Okay, second part to a boundary value problem is the governing equations. Okay. So the governing equations, in a nutshell, these are the differential equations that govern the physical behavior of your system. So every physical system has its own governing equations, okay? Whether it be a structural system, thermal system, fluid system, electromagnetic system, there's some differential equations that govern the system, okay? So it's always useful to think about, what is the most important physical behavior that I'm interested in solving for in this problem. which, again, seems like kind of an obvious question. And in a lot of cases, it is fairly obvious what you're going to be interested in, okay? But a lot of kind of really interesting engineering problems, often involve multiple equations, okay? And, those equations aren't really added in by default. You have to kind of manually add those equations yourself. So for example, I'll give you kind of kind of one of my favorite examples to give in this case. So, oftentimes, a structural simulation will be paired with a thermal simulation. Okay. So if you have, a situation where you have a part that's being exposed to some kind of physical loads, forces, pressures, but there may be some heating element involved as well. So maybe the part's being heated as it's going through its thing, or maybe it's being cooled, right? And so, one thing that that's well known, especially for metals, is that if you heat up a metal, or if you cool down a metal, the temperature of the metal itself will determine, its stiffness, its strength, its material properties, right? That's kind of how blacksmithing kind of works in general, right? And so in order to make a metal kind of malleable and easy to shape, you can heat it up to kind of extreme temperatures, then you can kind of shape it much easier than a cold piece of, right? And so if you have a situation, or if you have, an application where, heat transfer is going to be a big thing, but also structures, you need to kind of couple these two types of analysis. And it's not automatic either. And so, in ANSYS, you actually need to manually specify that, I have thermal situation, I have thermal considerations going on, and I have structural considerations going on. Okay. The activity that we did last Thursday, we only considered structural considerations. So if there was any heat transfer, we would need to add that in. Questions? Can ANSYS combine both? It can, yes. It is possible to combine both, but you have to kind of manually kind of specify. So, and so from kind of the project, in Workbench, you would load in a structural analysis and a thermal analysis, and then couple them together. Yeah, we'll talk about that kind of later on. So that's why it's useful to think about the governing equation. So if you have multiple types of physics going on, you need to actually account for that in your analysis. Okay? And so when you're thinking about your boundary value problem, think about, what are all the relevant physics. Oftentimes fluids is going to be something that's important too. Fluids and thermal are often two that are combined together a lot. Electromagnetism, not always. That's kind of the weird second cousin. We don't deal with that too much as mechanical engineers, but sometimes that could be a thing too, because magnetic forces that could affect what you're doing on the structural side as well. So last thing I'll say is you have to load in. Yeah, I think in ANSYS they're called analysis types or analysis systems. Actually, let me list a few here just for completeness sake. Okay. So the one we'll probably use the most commonly in this class is what's called static structural. Okay. So static structural is a structural type of analysis that's static, and so that essentially means that it's not changing with time. Okay. Another common one that's used is what's called steady thermal or steady state thermal. Okay. So again, this is a thermal situation, which is not changing with time, hence the name, okay? But the thermal means that you're going to be solving the heat equation, okay? Okay. Another one that you can do in ANSYS is fluid flow. Fluid flow is actually interesting because it uses kind of a different software called Fluent in ANSYS as well. I do have a handout on it, although I'm not super familiar with Fluent. I often use another tool for CFD, but it is possible to do fluid flow within ANSYS. Okay. And like I mentioned, there is electromagnetism. That is possible within ANSYS as well. I will say that I've never tried it in ANSYS before, just because, I'm not an electrical engineer. But the capability does exist to do that type of analysis. Okay. And also ANSYS has the ability to do time varying analysis as well. So not just steady, not just static analysis, but things that actually change with time. And so there's transient structural, there's transient thermal, there's transient, well, fluid flow is always transient, but you can do transient electromagnetism as well. Okay. So technically, there's a separate transient one for each of these. So, there should be, number 5 should be transient structural, number 6 should be transient thermal, number 7, transient fluid, and then transient electromagnetic. So, there's transient versions for all of them. So, next time we open up ANSYS, if you're not done with the first activity, open up ANSYS, and you could see on the left, you could see there's, probably about, I would say maybe 30 different analysis systems there. So there's a lot within ANSYS itself. And so choosing the right analysis system, choosing the right governing equations, especially when you have multiple types of physics going on, is something that's really important. Okay. All right. Any questions on governing equations? Yes.
You mentioned that you don't use Fluent. Is the program you use better suited for your application?
Yeah.
Solver different?
Right. So my research personally is on blood flow. So I use basically like an open source software called Synvascular to do this. So people have used Fluent for blood flow, but I'm just more familiar with Synvascular, so I've used it. Okay. All right, and so let's get to the last aspect of a value problem, which is what actually gives the boundary value problem its name, which are the boundary conditions. So boundary conditions, like I kind of alluded to back when we were talking about the domain, boundary conditions are only really applied on the extremity or the exterior of the domain. Okay. In particular, boundary conditions basically describe how the exterior parts of our domain are going to behave from a solution point of view. Mathematically, boundary conditions are required. And so if you kind of remember from your previous math class, whenever you have a differential equation, you can only solve that differential equation up to an arbitrary constant or arbitrary constants. And then to get the full solution, you need to apply the boundary conditions. Okay? So there are mathematical necessity to actually solve the differential equations. Just because you did use FE, it doesn't get around that. But I would say kind of from a more conceptual point of view, I like to think about boundary conditions as basically the outside world or any kind of external factors interacting with your subject, interacting with your domain. Because when you design a CAD file, when you design kind of a geometry to be used in ANSYS, when you look at the geometry by itself, it kind of, when you're just looking at the CAD file, it looks like the part is kind of just existing within a vacuum, right? You just model just the part itself, but in reality, that part is going to be put in some kind of larger physical system that's going to be interacting with its environment, and so there are going to be places where that your part is going to be fixed. It's not going to move. There's going to be external forces, external loads, pressures being applied to it. Okay. The way that you represent these external factors, the way that you model them is through the boundary conditions. Okay. And so, boundary conditions alongside with meshing, boundary conditions is something we're going to be talking about a lot in this class, just because boundary conditions, those are, probably one of the most important things that determine the accuracy of your simulation. Okay. And for me, I generally separate the boundary conditions into two main types. And so the first type of boundary condition that I like to describe is what's called constraint type boundary conditions. And the other type of boundary condition are load type boundary conditions. Okay. And both of those have kind of different conceptual and different mathematical ways that they're applied as well. Okay. So one thing that I kind of want to highlight here is the kind of the interaction between the boundary conditions and the governing equation, at least from a conceptual point. Okay. And so conceptually, you can think of the boundary conditions as kind of the inputs to our boundary value. And I'll explain what that means in a second. And what I mean by inputs is that, the boundary conditions, in most cases, the boundary conditions are the things that actually cause some interesting behavior to occur within the physical system. Because without boundary conditions, actually, without boundary conditions, every physical system is actually very boring. It actually doesn't do it. Okay. Let me give you an example. So, that book right there that's sitting on that table, right now, has no boundary conditions being applied to it, other than the fact that, it's being held up from gravity. So the only force being applied on is gravity, and there's a normal force that opposes it, and so that's why it's just kind of sitting by itself, right? By itself, it's very boring. Now, if I were to go up to that book and just karate chop it with all my might, probably nothing will happen because, I'm very weak. But, say a very strong person went up and karate chopped that book, that's going to cause some interesting things to happen, right? That karate chop is some kind of external effect for the boundary conditions, okay? So, a lot of times, when you're talking about kind of from a finite element mathematical point of view, the boundary conditions are what's, it's thought of as the input, because without the boundary condition, things are actually quite boring, nothing much really. Okay. So when you apply boundary conditions to a system, the system is going to oftentimes respond in some way. Okay. Now, how the system responds is often governed by the governing equations. Okay. And so you have kind of, boundary conditions, think of those as the instigators. I think of those as kind of the things that are causing some behavior, and the governing equations will determine how your system will respond. Okay. Part of the governing equations, of course, are going to be things like the material properties. The material properties kind of modify your governing equations, or they kind of change the magnitude of certain terms. But if you think about your FEA, or you think about your boundary value problems as this kind of cause and effect, or cause and response kind of relationship between the boundary conditions and the governing equations and all that's happening within your domain, it kind of helps to kind of frame a lot of the things that we're kind of doing. Okay. Any questions on boundary conditions? Okay. All right. So next thing I want to talk about is this idea of a primary solution variable. Okay. So, like we've talked about today, an FEA is nothing more than just a differential equation that we're solving in a computer, right? So it transforms from an algebraic equation and so on and so forth. Okay. When you solve a differential equation, there's usually one quantity that you solve for first, right? And so the primary solution variable is, whatever quantity or whatever, solution that is solved for first in a boundary value problem, or the governing and differential equations. Okay. There's always something that's solved for first. And I think this kind of gets lost in the wash a little bit when you're using a tool like ANSYS, and it kind of shows you all the results at once. Okay. But, under the hood or mathematically, there's always something that has to be solved for first. And then usually a lot of other quantities are solved for after that. Okay. So let me give you an example. Okay. In static structural, right? there are lots of different outputs, or there's lots of different results that you can show from your FEA simulation, right? And so you can show things like the total deformation. You can show things like the equivalent stress. Okay. And I'll throw one more on there as well. Well, you can also show the equivalent strain. Okay. And even within some of these types of results, there are a lot of subcategories as well. So you can show principal stress. So I know some of you probably did that for activity one as well. Principal strain, you can show deformation in different directions. You can show stress in different directions, right? You can show factor of safety, things like that. Okay. So before all of these quantities, there's something that's actually solved for first. Okay. Which is the primary solution variable. So the primary solution variable in structural simulations is the deformation. And so whenever you're running a type of governing equation, it's always useful to think about, what is your primary solution variable, right? If you're running a thermal simulation, the primary solution variable there is temperature. If you're running a fluid flow simulation, the primary solution variable is velocity. For electromagnetism, I actually don't even know. I think for electromagnetism, it might be the electric field. I'm guessing everything is derived from there. Okay. All right, and then all the other results that you see, and sometimes it could be a lot, sometimes it could be a couple dozen, which is the case for structural. Okay, everything else is what's known as a derived quantity. And so a derived quantity is not solved directly from the governing equation. It's not solved directly from the FEA. A derived quantity is computed after you compute the primary solution variable. And so kind of the order of operations that first your ANSYS or your FEA is going to solve for the primary solution variable, and then it's going to take that solution and then solve for all of the derived quantities after that. Okay? Okay. So other common ones, factor of safety. Factor of safety also is a derived quantity. Okay. So why is this relevant? So generally speaking, your primary solution variable will be computed fairly accurately, or the accuracy of the primary solution variable will be the highest. Okay. So if you're running a static structural simulation, you can probably trust that the total deformation, at least compared to the other types of results, your total deformation, that's going to be the most reliable. Okay, it may still be wrong, but it's probably the least wrong out of everything. And then all your derived quantities, their accuracy or their reliability is going to be low. Okay, so later on in this class, we're going to talk about the concept of a mesh convergence test, which basically tests, how accurate or how reliable your solution is relative to the mesh that you have. Okay, and what you're going to see, and what you should see basically all the time, is that your primary solution variable should converge first compared to your derived quantities. Okay. That's going to be important because you want to kind of ask yourself, what is the primary output, or what's the primary variable that I'm interested in the simulation. And so you don't want to kind of trick yourself and say, I'm interested in the stress, But if I run my convergence test on deformation, I don't want to trick myself into saying that this is more accurate than it is. Okay. So it's always useful to kind of be aware of kind of what your primary solution variable is when you're talking about reliability, accuracy, things. All right. Any questions on this? Okay, so one last thing before we wrap it up for today is I want to talk about the concept of element stiffness matrices. Now, we're not going to go fully into element stiffness matrices. For those of you who have taken 541 or 410 with me, this is something that we talk about for weeks. It takes a long time to get used to. But I at least want to kind of show you, because I think understanding what the element stiffness matrices are will kind of give you an appreciation of, what's the difference between a mesh with, 1,000 elements versus a mesh with, 1,000,000 elements. Okay. So the idea with an element stiffness matrix is that, whenever you run a finite element simulation, each element in your mesh kind of represents a mathematical system on its own. So every single element in your mesh, will have a system of equations that mathematically describes its behavior. It basically takes your governing equations and applies it on that little kind of tiny mesh or that little tiny element. Okay. So, if you have kind of a mesh, let me go ahead and draw the geometry for our activity 1 again. Okay. And so let's say that you have a mesh that looks like this. Okay. Okay. So each element here in this, red waffle that I've drawn, each element there has a system of equations that govern its behavior. Okay. So if I look at, this element right here, let me go ahead and bring it out. That small square, has its own system of equations that governs its behavior. Okay. Now, if you've taken 541 with me, you may think like, oh, that square probably has I don't know, maybe a 4x4 system of equations that governs its behavior, right? And so that's basically 4 equations and 4 unknowns. So you multiply 4 equations, 4 unknowns by, maybe this mesh has 1,000 elements. So that means there's 4,000 equations and 4,000 unknowns. Okay. Well, the FEA that we did in 541, was kind of a beginner's FEA. So in reality, for something like this in ANSYS, each element probably has somewhere close to, I would say maybe 16 to 20 different equations and unknowns associated with it. Right. And then you take that and you multiply it by, 1,000, 10,000, 50,000 elements that you have, and you can see things start to kind of get out of hand very quickly. Okay. Eventually, what happens is that, for each element here, all of their individual systems are going to get combined into one massive system of equations. Okay. And so this system of equations is what I call the global linear system. And the global linear system will have contributions from every single element that's in the mesh, okay? So basically, every single element is going to contribute to the global linear system, okay? And again, in this class, we're not going to go through this, and so, that's 541. If this, for some reason, excites you and makes you want to learn more, then you can take 541 with me. It's probably not a very fun part of the class. You can ask the people who have taken it already. But, it becomes a very, very messy procedure, okay? And so, this is just to kind of illustrate to you that the more elements that you have in the mesh, it really adds a ton of cost to the entire job. So, each element that you can think about, each element that you add to your mesh adds, anywhere between, 20, 30 equations to the entire system. So, it gets pretty out of hand. Okay. All right. Any final questions on this before we wrap it up for today? Okay, all right, so it's a little bit early, but I don't have anything else to talk about. So instead of stalling for another 8 minutes, I'll let you guys go. So thank you guys for coming today. When we come back on Thursday, there's gonna be another lecture. So I believe we'll be talking about meshing on Thursday, but I need to check the schedule just to be sure. And remember your ANSYS activity to do this week as well. So if you have questions on the activity, don't be afraid to ask. Send me an email. I do have office hours one more time, so I don't have office hours tomorrow. But Thursday I do have office hours in the afternoon, so or you can just send me. Okay. So thank you guys for coming today. Hope you guys have a good rest of the evening, and I will see you guys on Thursday. Bye.
Yeah.
Okay.
My definition, I think.
You want mine?
Okay.
But
I think
my,
was your answer wasn't home?
It's literally, I'll show you, it's doing it here, I just think it's.
Oh, yeah, well, I mean, for this one, the whole was only put on, so that's gonna make it all. But, I can actually mention today, so the stress is a derived quantity, so that's always gonna be a little bit more,
Try to do it at home.
not as accurate as it is. And so there's always gonna be differences, especially with relative to the mesh. And so even though the colors may look different, I think the actual value is very close. Because what happens when you change the mesh a little bit, is like the max is something to do. And so that, it might be a little bit different from the other. So that's gonna change how the colors kind of display.
so, I feel like don't have that, but I think that's still okay.
Oh, yeah. Well, I mean, this one and this one are gonna be very different. The whole is much bigger.
Okay.
Yeah,
So we're gonna go with that.
exactly. Yeah, I wouldn't worry about it. For this one, the results are pretty.
Yeah, Gary.
I can do this one, that was literally.
It might, well, I don't know if it's that, but that
Do I have to-
seems like it'll, there you go. Dude. Put on it. Hey, that was sorry, that was
I have to say this. It feels true, but I was like, I'll do that. Something wrong wherever. It's like.
It'd be like that.
I was actually thinking. Look, I've done this like twice already. That was just like, no.